Hello, I'm Fleshed Out Thoughts, and I love fleshing out thoughts for extended periods of time. And I'm currently building a full stack e-commerce platform for digital products and software services with Next.js and Supabase. This series is about the architectural decisions behind the platform, what I built, why I built it that way, and what I do differently. Today, we're going to be getting into API contract design for Next.js server actions. Okay, so to start out, a server action is not an implementation detail. It is a publish interface. Every component that calls it depends on its name, its argument shape, and what it returns. Change any of those things without a plan, and you'll break callers. The failure mode is subtle. You resume a field, your TypeScript compiler doesn't catch it because the call site was using object.from entries on a form data object. You deploy. A form stops working in production. You spend 40 minutes triangulating between a generic something went wrong error and a stack trace that points to a database call, not the field mismatch that caused it. This video is about avoiding that. For my e-commerce platform built on Next.js and Supabase, I use these 3 rules that work as a system: business intent naming, Zod input validation, and a discriminated union return type called ActionResult. Together, they define what I call the contact-first approach to server actions. I'll walk through each rule, share the expand contract migration pattern for evolving contracts safely, and cover idempotency keys for financial operations. As you see on the screen, here's what I used to write. No input validation, ambiguous field names, throws on error, and the response shape is whatever the database returns, which name it can change without warning. Here's what breaks. Rename one field and every caller needs updating manually, with no compiler help, because you're working with untyped form data. Change the response shape and you get silent, undefined in the UI. Neither of these errors are loud. They're the kind of discover when a user files a support ticket. The most expensive one hit me personally. 40 minutes debugging a production issue where one code path returned a specific shape that differed from another. Same action, 2 different callers, 2 different shapes, neither caught at compile time. The decision at the bottom of this slide is one of that drives everything else. Server actions are not implementation details, they are published interfaces. Every name, argument, and return type is a promise to callers. Here we are. The contract first approach. 3 simple rules that work as a system. Remove any one of them and the others are weakened. 3 rules to follow and they work as a system. Remove any one of them and the other 2 weaken. Rule number 1, business intent naming. Create order, cancel order, refund order, not update order, process order, handle order. These names describe what the user is trying to accomplish, not what the code does. This matters because a server action name is a stable identifier like a URL. You show it in logs, reference it in audits, search for it in your code base. A vague name is permanently vague. Rule 2, Zod input validation. Every action receives a typed validated object. If the client sends something unexpected, a string where an integer is expected, a missing required field, the action rejects it before any business logic runs. The Zod schema is living documentation. It can't go stale because it's enforced at runtime on every call. And the 3rd rule, discriminated union return types. Action result, either these shapes here. The client pattern matches on OK. The action never throws. The error is always machine readable. The decision line says it clearly. 3 rules as a system. TypeScript types become the documentation. No README to maintain. Naming, the cheapest improvement. Naming is the cheapest improvement available because it costs nothing to do it right and compounds continuously. Look at the before column. AMT is that cents or dollars. Type, product type or parent type. Flag, false means what exactly? Update order, what operation? Cancel, confirm, refund. TS, epoch, ISO, which event? Every one of these is a question a future developer or a future you at 2 a.m. will have to answer by reading the implementation. The name transfers no information. The after column eliminates the question, total amount minor units. Unambiguous. Product type distinguished from payment type. Requires shipping address. The Boolean is self-describing. Cancel order and confirm order. Separate functions for separate operations. Created at and paid at. The at suffix signals a timestamp, and the event name tells you which one. The rules that produce these names. Booleans start with is, has, can, or requires. Timestamps end with at. IDs end with ID. Action names are verb, noun, camel case. These 4 rule covers most of the naming decisions you'll encounter. Every server action on my platform follows the same 3-step life cycle. Validate, authorize, execute. The SVG shows this. A request arrives. Step 1, Zod validates the input. If validation fails, a structured error is immediately returned before any authorization check, before any database call. The error includes a machine-readable code the client can render specifically. Step 2, authorization. Supabase row-level security runs here, or an explicit check against the user's session. If the user isn't allowed to perform this operation, another structured error is returned. Step 3, execution. The business logic runs, database writes, Stripe calls, email queuing, and the result is returned as action result. The validation, first order matters for privacy. Malformed input is rejected before the system touches any user data or logs anything sensitive. And it means structured rejection reasons without details. Useful for both UX and security. The rule, every action follows this pattern. No shortcut. Internal actions follow the same pattern as external ones. Consistency is the contract. The left side shows Zod schema for place order input, items array with product ID and quantity, both typed and constrained. Shipping address ID as a UUID, idempotency key as a UUID. The key insight is the comment at the bottom, wrong type or missing field, rejected before any DB call. The schema is the documentation. It's always accurate because it's enforced at runtime on every invocation. The right side shows action result, 2 branches, success and failure. 4 fields in the error object. Code is a string constant like card decline. The client switches on this. Message is human readable for display. Retryable tells the client whether it's safe to try again automatically. Request ID is the forensic trail, a unique identifier that connects the user's complaint to the exact server log entry. Never throw from a server action. Always return. Throwing bypasses your return type, strips the structured error, and gives the client a generic HTTP error to work with. Without structured returns, the database throws, the error propagates up, and the client sees internal server error. No code, no context. The developer sees a stack trace in the console. No user context, no way to know what the user was doing or which order was involved. With structured returns and request ID, the failure is explicit, useful, and traceable. The client gets a specific error code it can render as a specific message. The user gets that product is no longer available instead of something went wrong. And when the user files a support ticket, they paste the request ID. You grep for that ID in your logs and you're there immediately. The decision, Never throw from a server action. Always return request ID in every error. That ID is the bridge between a confused user message and your full server context. The expand contract migration pattern. The atomic rename is the footgun. You rename a field in the server action. You rename it in the caller. You deploy it both in the same release. Between the moment the new code deploys and the moment the old client's browser tab still opens from previous deploy, refresh, there is a window. In that window, old callers send the old field name and the action rejects them. Expand contract eliminates this window. 4 phases, each deployable independently. The first phase is expand. Add the new field as optional. Write to both old and new. Deploy. Old callers are unaffected. They keep sending the old field name and the action writes both. Backfill. Populate the new field for all existing records. Verify data integrity before proceeding. Migrate. Update all consumers to read from the new field only. Monitor until you've confirmed 0 reads of the old field. Remove the old field. The contract. Remove the old field. Migration complete. Breaking change risk virtually 0. The decision, expand, contract over atomic renames. New code deploys before the migration runs. There is always a window. 4 phases, each independently deployable. Idempotency keys for financial operations. The client generates a UUID before submitting. It passes that key with every request. The server records the key when it processes the request. If the network drops and the client retries with the same key, the server recognizes it and returns the same result without charging the card twice. That's the basic mechanic. The debugging payoff is what makes idempotency keys worth adding even at small scale. 4 questions collapse to 1 table query. Did Stripe fire the webhook twice? Check the idempotency table. Is the key present twice? Did the network retry the request? Same key? Yeah. Different key? No. Did the user double-click submit? Same key from the session? Yes. Was there a duplicate charge? 1 table query, deterministic answer. Without idempotency keys, answering any of these requires triangulating through Stripe's dashboard, your server logs, your database, and your email outbox. With them, 1 query. Should I use server actions for reads? No. Use React server components or route handlers for reads. Server actions are for mutations. Mixing reads in blurs the distinction between what changes state and what reads it. Why do I handle validation errors? Well, with Zod's safe parse, it returns a structured error array that maps back to individual form fields. Never throw validation exceptions. They bypass your structured return type and leak implementation details. Can I version server actions? Not with a URL. They are RPC, not REST. Version with function names. Create order v2 alongside create order. Deprecation means a code comment and notifying callers. Expand contract applies to the schema too. Why not TRPC or REST? TRPC is excellent if you're already using it. The same contract principles apply. REST makes sense when you need public API consumers. Server actions are the right default for Next.js where client and server are the same code base. The summary, right? The contract is a promise. 5 key takeaways from this video. Name actions after business intent. Create order, cancel order. The name survives longer than the implementation. A vague name is a permanent tax. Validate inputs with Zod. The schema is the documentation. Always accurate because it enforces at runtime. No readme to maintain. It is always accurate because it is enforced at runtime. Return structured results, never throw. Put a request ID in every error. That ID is your forensic trail for user complaint to server log. Evolve with expand contract. Never rename atomically across a deployment boundary. The window is always there. 4 phases, each independently deployable. Use idempotency keys for financial operations. 1 table query replaces 4 source log triangulation. The debugging payoff alone justifies the cost. For a client, API contracts on this platform are versioned and migration safe. Schema changes follow, expand, contract, preventing breaking changes from reaching callers. A client building integrations can rely on contract stability and can trace any error back to a server log with a single ID.